let's review for this test, guys. Listen, one of the first things that we talked about in this chapter was tangent lines and what's called like anytime you see the word like approximating with a tangent line. So sometimes we call this local linearization because it's like, sorry, I'm not writing very well. Linearization. Okay, because it's like approximating something with a tangent line, and so there's linearization, and then it's like, oh, I'm going to approximate it right here when it's really right there or whatever, right? So if you see the words local linearization, if you see the words like approximate, this is what we're going to do, all right? So this is something you guys need to know. Write this down, memorize, whatever. Your equation that you're going to use for all of these is y minus y1 equals mx minus x1. So for number one, it says if y equals, y equals x over x plus 5, right? Find the equation of a tangent line when x is negative 6, and then use it to approximate negative 6 1/5. So let's just start with the first part. Find the equation of a tangent line when x is negative 6. So the first thing I would want you guys to do is write down this equation here. Y minus y1 equals mx minus x1. Start filling things in. So y minus, right here is the y coordinate, m, and then x minus the x coordinate, and that's what I got to fill in. Well, it gave me the x coordinate, and the x coordinate's negative 6. Now, it did not give me the y coordinate, but if I plug this in, I can find the y coordinate. When I plug that in negative 6, I get negative 6 over negative 6 plus 5, negative 1. So the y coordinate is 6. Okay, and then I need to find the slope. And you guys know the slope is the derivative, okay? So let me take this right here. Let me do a derivative. This is going to be a quotient rule, okay? Derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. So this gives me, you know, these are just ones, but if I were to like distribute that, this gives me x plus 5 minus x. And then those x's cancel out. So it's 5 over x plus 5 squared. Okay, and if I am trying to find the equation of a tangent line at negative 6, let's go ahead and plug that in. So that's going to give me 5 over negative 1 squared, which will just be 5. Okay, equation of tangent line. There we go. Okay, so let me write that a little bit better. So it's a y minus 6 is 5x plus 6. That's my equation of tangent line. Then it says use it to approximate the y coordinate when x is negative 6 1/5. Okay, so check this out. The approximation for x is negative 6 1/5 is just plugging that into the tangent line. Instead of like plugging it into the regular function, I plug it into the tangent line, okay? So I get y minus 6 equals 5, and then I get negative 6 1/5 plus 6. Negative 6 1/5 plus 6 is negative 1/5. Times 5 is negative 1. And if I add the 6 over to both sides, y is 5. Okay, so that's my equation of tangent line. That's my approximation at negative 6 1/5. Okay, let's go ahead and look at number 2. Use the data in the table shown to find a linear approximation of 4.2. Okay, so again, I'm using the data, and I'm using this line. Let me go over here, and let me get my data table here. Okay, y minus y1 is mx minus x1. Now, if I can figure out what all these things are in the table, then that's great. There's my x coordinate. So that represents my x coordinate. What does that represent? G of x? That represents my y coordinate. Okay, that's my like y1, that's x1. And what does g prime represent? Slope. So it's really easy. It gave me all this information, right? So I can come over here and I can say, okay, my equation of the tangent line is y minus 3 equals mx minus 4. Okay, there's my equation of the tangent line. Now use that to approximate 4.2. Well, y minus 3 is negative 2, 4.2 minus 4. So now I'm going to get y minus 3 is negative 2 times 0.2. So that's negative 0.4. And then if I add 3 to both sides, y is 3 minus 0.4, which is 2.6. So there's my approximation. Okay. By the way, I wanted to show you guys something. I added something new on to make this smaller so you can see it. Canvas, where, hold on a minute. I uploaded all the solutions, and I'll start doing that for chapter. We just got to remind me. So the solutions to all the different stuff. So all the review answers are on there too. Okay. Okay. Anyways, let's get going. Number 3. All right, this looks fun. Okay, I'm going to draw a picture here. An interstate driver traveling 420 miles across state from south to north without stopping. An interstate driver, 420 miles. At noon, she notices her speed is 60 miles per hour. And her position is at 240. Interstate miles increase. Okay, that's fine. Use this data to write a linear localization which could be used. So again, you guys, I'm sitting here like, what the heck? Right? Estimate her position as a function of time, assume time equals 0 at noon. So maybe you're sitting here going like, dude, I have no clue. Like, what am I even supposed to do? That's fine. The second I see the words local linearization, I'm writing this. Okay? And it told me that noon is times 0, and so that's going to be my x coordinate. And at time 0, now which of these is mile marker 240 and 60 miles per hour? Which one is more of a rate? Well, this one's more of a rate, so that's a derivative. That's probably my y1 because at time 0, I'm at mile marker 240. So I'm going to write it like this. Y minus 240 is 60, x minus 0. Again, I'm just kind of trying to figure out, like, that's my local linearization, okay? Approximated position at 2 p.m. All right, so here's my thing. Okay. Now, to answer the next 2 questions, 2 p.m., if noon was time 0, 2 p.m. is time 2. 10:30 a.m., if noon is 0, 10:30 a.m. is an hour and a half before that, so it's negative 1.5. Okay? So that's how we can get negative time, is just saying, like, before my starting time. Okay, so let's go ahead and do those 2. So with the tangent line that I came up with, y minus 240 is 60, 2 minus 0. So 60 times 2 is 120, so 360. So at 2 p.m., I'm approximating it at 360, okay? Y minus 240 is 60, and negative 1.5 minus 0. So 60 times negative 1.5 is negative 90. And so when I add that over, y is 150. So at 10:30 a.m., I was at mile marker like 150. Okay? And then the last thing says, what's your domain on which the linear function can be applied? That's a little bit tricky, but let's see. If she's going 60 miles an hour, and this is like time equals 0, she would have started 4 hours before that, because 240 divided by 60, right? And if we keep going to 420, 420 divided by 60 is 7. That's a total of 7 hours, so 3 more hours that way. But because I let time 0 be right in the middle, my domain is, she went from -4 to 3, which is really like noon minus 4 is like 8 a.m. to 3 p.m. Okay, but it's just a way of like writing that out. All right, so local linearization, hopefully you guys are okay with that. Just write the equation of tangent line and you should be all right. Okay, next we're looking at the limit questions. And the next big thing, remember that we learned on our, I think I have enough room to do these here, that we learned in this chapter was L'Hopital's rule. No, L'Hopital's, right? L'Hopital, which says, if I plug this in and I get 0 over 0 or infinity over infinity, I could take the derivative of the top, the derivative of the bottom, and try it again, right? So let's look at number 4. And I plug in pi over 2, okay? Now, the sine of pi over 2 is 1. So I get 2 minus 2 and pi over 2 minus pi over 2. So I do get 0 over 0. So I'm going to do L'Hopital's rule. Okay, which is going to say, okay, so I'm going to do the limit as theta approaches pi over 2. And when I take the derivative of the top, you guys, the derivative of 2 goes to 0. The derivative of sine is cosine. And when I take the derivative of the bottom, the derivative of theta is 1 and the derivative of a constant is 0. Okay, so I get that. Now when I plug it in, the cosine of pi over 2 is 0. So now at this point, I can go ahead and plug this in and I get -2, the cosine of pi over 2 is 0, over 1, which just gives me 0. Okay, let's go ahead and look at number 5. When I plug in pi over 2 right here, all right, so let's say I put in pi over 2, pi over 2. Okay, the cosine of pi over 2 is 0, so I end up getting 2 minus 0 over pi over 2. This is not a L'Hopital's question. This is a direct substitution question, right? So basically my answer is 2 over pi over 2, or if I multiply by the reciprocal, my answer could be 4 over pi. Okay, so that's okay. But that's not a L'Hopital's question. That's direct substitution. All right. Okay, for number 6, if I do infinity, e to the infinity is still going to go to infinity, and infinity squared is going to go to infinity, so I do have infinity over infinity. Okay, so I'm going to do a L'Hopital's rule. So I'm going to say, okay, this is the same as the limit as I approach infinity of, the derivative of the top is just e to the x. The derivative of the bottom is 2x plus 1. When I try to plug in infinities, I still get infinity over infinity. So I'm going to do it one more time. One more L'Hopital's rule. The derivative of e to the x is e to the x. The derivative of 2x plus 1 is 2. Now this time when I plug it in, you guys, I end up getting infinity over 2, which is infinite. Okay? So this does end up going to infinity. Another thing you could think about from the beginning is the growth rates of these. We know that x squared grows not nearly as fast as an exponential, and e to the x grows way faster. So it's going to approach infinity because it grows faster. So you can do it that way too. Okay? Okay, perfect. Number 7. Let's see. ln of infinity is infinity. Infinity plus 2 is infinity. So again, you could talk about growth rates, or we can do L'Hopital's, right? Limit as x approaches infinity. Okay, the derivative of ln is 1 over. The derivative of x plus 2 is 1. Now, you guys, if I try to, I mean, you can't really plug in infinity, but if I try to evaluate, 1 over an infinitely large number is 0. And 0 divided by 1 is 0. The other way you could think of it is x grows faster than ln. So there's a page in our books toward the beginning that we talked about like different growth rates and what grew faster than other things. So you could think about like let's see here, e to the x grows very, very fast. X squared, not quite as fast. This will get to infinity much faster, right? Square root x grows very slow. It still goes to infinity, but it grows very, very slow. And like ln x, where's my ln here? Ln of x, again, also goes to infinity, goes very, very slowly. All right, so there are different ways to get to infinity. These are all ways to get to infinity, okay? It's just that you got like fast ways to get there and slow ways to get there, okay? And this is x gets there faster than ln, so that goes to 0. All right, let's see. These both go to infinity. Now, I could do L'Hopital's rule, you guys, 4 times. Okay, I could. You don't have to write this down. Just look. It's like 20x to the third minus 6x, that goes away. 4x to the third plus 3, that goes away. And then it's like, oh, it's still infinity over infinity, so then I do it again. Let's see here. 60x squared minus 6, and that's 12x squared. It still goes to infinity over infinity, so I do it again. 120x, that goes away, over 24x. Still goes to infinity over infinity, so I do it again. 120 over 24, which 12 and 24 reduces to 1 and 2, so that looks like that equals 5. Okay, that's a long way to do it. I taught you guys how to do these in our very first chapter. So instead of doing L'Hopital 4 times, right, could you guys just remember that I talked about how if the degree of the top and the degree of the bottom are the same and it's approaching infinity, what is this going to go to? It's going to go to 5. Because the degree, it's going to go to coefficients. All right, so you can do a crap ton of L'Hopitals, or you can just recognize, yeah, that's going to go to 5. Okay. Let's see here, last one here. Let's look at, if I plug in 2, I get 3 times e to the 0, which is 3 minus 3. And if I plug in 2, I get 8 minus 8. So this goes to 0 over 0. All right, cool. So I'm going to go like this. I am going to do a L'Hopital's rule. Okay, the derivative of 3e to the x minus 2 is 3e to the x minus 2. That goes to 0. The derivative of 4x plus 8 is 4. Now when I sub it in, I get 3e to the 0 over 4, but e to the 0 is 1, so I get 3/4. Okay? All right, cool. So that's how L'Hopital's works. So any limits questions you have, well, you have to decide if you can use L'Hopital's or not. All right? All right, perfect. Next little section here. Number 10, using the graph and table above, find the following limit. Now, you guys know that the first time we do a limit, like limit of as x approaches 4, I just plug in. I do what's called direct substitution, okay? So I'm looking for what's f of 4, and then what's 2 times g of 4 minus 6. All right. F of 4, if I find it on this table, or on the graph, I mean, f of 4 crosses at 0. G of 4, tells me it's that right there, is 2 times 3 minus 6, which is also 0. So this is a L'Hopital's question, okay? So I'm going to use L'Hopital's. And I'm going to write it up here, but let's take a look at this. Okay, I'm going to L'Hopital it right up over to here. All right? So still the limit as x approaches 4. But now the derivative of the top is f prime. The derivative of the bottom is 2g prime, and the derivative constant is 0. Okay? So now that I have that, I got to go figure out what f prime of 4 is, because I'm going to do direct substitution here. So I'm going to do f prime of 4 and 2 times g prime of 4. Maybe I can get 0 over 0 again, or maybe I'll get an answer, right? Okay, f prime of 4, when you're looking at a graph, f prime means the slope. So that means what's the slope at 4? And if I look at this slope here, this goes rise over run. It looks like it goes up 2 over 1. So that on the top is 2. And then if I want to find g prime of 4, well, it's just right there. So I get 2 over 2 times negative 2. So I get negative 2/4 or negative 1/2. All right. Okay. Now, really important. You guys need to know this for your test. Absolute extrema, or absolute max and mins. Okay. And mean value theorem. All right. So these are the things we need to know. Let me do absolute over here on this other page. Okay. All right, so starting with number 11. Absolute extrema of -1/3 x to the third plus x on the interval -2 to 3. Okay, one of the things that we talked about in class today, let's see if I can find where I wrote this down. Okay, stuff that you need to know for the test. Here we go. Absolute max and mins, you got to test critical points and endpoints. Okay, we have mean value theorem, we have tangent line approximations. But absolute max and min, we test critical points and endpoints. So let's go ahead and look at this question here. Okay, critical points are when I take the derivative, I bring that down in front, set that equal to 0, okay? So negative x squared equals -1 when I subtract it, divide by -1, and square root both sides. Now you guys, when I square root both sides here, I get plus or minus the square root of 1, which is 1. These are my critical points. These are my endpoints. Okay, and I'm going to do what's called the candidates test. I'm going to test these, right? So I have this table here. And I'm going to test my endpoints and my critical points. And where am I testing them? Well, I'm testing them into the original problem. Okay. Okay, if I plug in -2 to the third, that's a -8. So that's going to end up being 8/3 minus 2. Should I figure out what that is? Sure. 8/3 minus 6/3. So that's like 2/3, I think. Okay. All right, if I plug in -1, that gives me 1/3 minus 1. That's -2/3. If I plug in 1, I get -1/3 plus 1. That's +2/3. And if I plug in 3, I get 27. I get -9 plus 3. I get 12. Okay? So look, guys. That's my absolute max. That's my absolute min. All right? So I can find them just by doing that table and then just finding the highest number y value and the lowest y value. Okay? Let's see. All right, I was going to check my answers, and this is why. Come on, Mitchell, because I'm being dumb. Hold tight a second. Did you guys catch this mistake here? Oh, yeah. All right, when I plug in 3, I do not get 12. Let's try this again, okay? When I plug in 3, 3 to the third is 27, so I get -1/3 times 27 plus 3. So I get -9 plus 3. I did 9 plus 3. I was doing it too fast in my head. Okay, let that be a lesson to you. Don't do things fast in your head like that. So anyway, this ends up just being -6. All right, so that changes everything, right? So my relative, or sorry, my global max or absolute max is 2/3. It occurs at 2 different places, but the max is 2/3. My absolute min is -6. Okay? That's why I check these. Make sure I'm not making dumb mistakes like I just did. All right. Cool. Let's find the absolute extrema of, my next equation is 3/2 x to the 2/3 minus x on the interval -8, 1. Okay? So step 1, critical points. If I bring that down, 3/2 times 2/3 is 1. And if I subtract 1, that's x to the negative 1/3 minus 1. Okay? Another way to write that is 1 over the cube root of x. And if I set that equal to 0, you guys, if I bring that over, so 1 over the cube root of x equals 1. So if I cross multiply that, the cube root of x is 1. And if I cube both sides, x is 1. X is 3. Okay, now x is 1. All right. And that's my only critical point. Let me just make sure I did this right. To do x to the negative 1/3. 1. Yeah, we're good. Okay. So my critical points, my critical point is at negative 1. Now, there's actually also one other critical point here, and this one is super tricky, but there is another critical point here. And technically, okay, critical numbers are where, let's see if I can write this down for you. Critical numbers are where the derivative is 0 or undefined. As long as that undefined point is still in the original problem. Now look, in the original problem, you guys, there's no undefined points. There's no dividing by 0 or anything. We're all good. In the original problem, it is continuous on this entire interval. But when I got to the derivative, there actually was an undefined point here. Can you guys tell where the undefined point is? Something that would make the bottom 0. X equals 0 is undefined, so it's still a critical number. Now, this is a very tricky thing to try to get. X to 2/3 minus x. Let's look at what this graph looks like real quick. Okay. 3 over 2, x to the 2/3 minus x. Is that what it said? I think. But anyway, yeah, so look. I have a critical point right here at 1, but I have another critical point right here at 0. Okay? Because it's undefined right there, but it's still changing from one to the other. The derivative is undefined there. And I was looking at the restrictions from, what was it, -8 to 1. I have to write like this. -8 less than or equal to x less than or equal to 1. Okay? So I can kind of see here, like, there's my absolute max, right? It's on the end point. That's probably my absolute min. Okay? So you can kind of see what it's talking about. So, yeah, this one, the trickiest part was to see that you actually had to use 0 also. So -8, 0, and 1. And when I do the candidates test, back into the original problem. All right, -8 to the 2/3. So minus -8. The cube root of -8 is -2. Squared is 4. 3 times 4 is 12. Divided by 2 is 6. So that gave me 14. If I plug in 0, 0 minus 0 gives me 0. If I plug in 1, 3 over 2 minus 1 gives me 1/2. So here is my absolute max, and here is my absolute min, which we can kind of see on here. Like, that was my max, that was my min. Okay? Yeah, geez, that was a tricky one. All right, next, yes, mean value theorem. Okay, I can fit these on here. Okay, mean value theorem, first of all, in order for it to even work, you always have to check if it can work or not first, okay? And in order for it to work, you guys, your function has to be continuous on the interval it gave you. And continuous means no asymptotes, no holes, no jumps, nothing like that. And it has to be differentiable. In other words, you could take the derivative on the open interval, meaning you don't have to do it on the endpoints, but everything in between. Okay, so when I look at number 13, I cannot use mean value theorem, and here's why. You guys see that, I'm gonna write right here, there is a vertical asymptote at x equals 0. And so f of x is not continuous on the interval negative 1 to 2. If it had been like positive 1 to 2, it's fine. But it has a vertical asymptote there, so that's definitely not going to work. All right. Okay, let's see about this one. Number 14, it also has a vertical asymptote. But this one has a vertical asymptote at x equals 3. And guess what? That's not in my interval. So I'm actually fine. I can definitely do mean value theorem on number 14. I'm okay because my vertical asymptote is outside of that interval. So between 4 and 6, it's continuous. So I can do that for 14. We'll come back and finish that problem in a minute. For 15, this is actually, you kind of have to know what this graph looks like, you guys. Okay, and we know that a regular absolute value graph looks like this. All right. Now, when I move this around, let's see, this is telling me I have to move it right 3 up 2. Okay. So check it out. Right 3 up 2. All right. So right here, this is the point 3, 2. All right. This I actually cannot use mean value theorem on. It's continuous and that's fine, but it's not differentiable at x equals 3 because of what? A sharp corner, right? So it's not differentiable at 3 and 3 is in that interval, so I can't do it there. So the only problem that I can actually do mean value theorem on is number 14. All right, so now let's actually do mean value theorem for number 14. Let me get this out of the way. Looks like that had a little issue. Okay, so here we go. When you're actually doing the mean value theorem, you want to say you're looking for where the derivative equals the slope, okay? Now for derivative, you're literally just taking this and taking the derivative. This is a quotient rule, so I'm going to go derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. So I get x minus 3 minus x and then these cancel out. Okay, so I end up getting negative 3 over x minus 3 squared. So that's derivative, right? Okay, now I'm going to do slope. Now for my slope, it's from here to here. So the slope from 4 to 6. Well, I need to go ahead and plug those points in to figure out what the y coordinates are. If I plug in a 4, you guys, the y coordinate is going to be 4 over 1. So that's 4, 4. Okay, if I plug in a 6, the y coordinate is going to be 6 over 3, which is 2. And so then my slope will be y2 minus y1 over x2 minus x1, which is negative 2 over 2, which is negative 1. Okay, so then for my last step, I want to set the derivative and the slope equal to each other and solve. I'm going to cross multiply, or basically I'm just going to take this and multiply it up on the other side. So I get negative 3 is negative 1 x minus 3 squared. Divide that over. So that gives me 3 is x minus 3 squared. Square root both sides. So x minus 3 is plus or minus square root of 3. And then when I solve for x, when I add the 3 over, it's 3 plus or minus square root of 3. Now I do have to check to make sure that those are in my interval. Well, look, 3 minus square root of 3, that's going to be something less than 3, so that's not going to work. So my c value is 3 plus square root of 3. And that's the value, remember, where the slope and the derivative will be equal. Okay? All right, nice. Let's see, 14, how many questions are there? Okay, great, perfect. That's exactly halfway. So let me stop this video and then I'll start the next one.